We've done a few examples here of finding limits, but so far, every time we found a limit, it actually existed. It turns out that's not always the case. In other words, our functions don't always have to approach a single real number as we get closer to a value for x. Now we're going to look at a couple of different ways that this can happen. The first way that this can happen is through a piecewise defined function. So here we have a piecewise defined function. I know a lot of you probably don't see the set brackets. Usually when we define a piecewise defined function, you put set brackets on one side and not the other. The computer program that I'm dealing with forces me to put set brackets on both if I want to scale them to the correct size. So that's why it looks like that. But this piecewise defined function, f of x, is defined in two parts. The first piece says evaluate x as x plus 2 for any x less than 3, and evaluate f of x as 3x minus 1 for any x bigger than or equal to 3. So we're going to use numerical and graphical approaches to find the limit as x goes to 3 of my function. So let's go ahead and do this numerically first. So just like always, 3 is a whole number. You might as well get a tenth away, and then 100th away, and then 1,000th away. See if we can establish a pattern. If I do that, I better get a tenth away on that side, and then 100th away on that side, and then 1,000th away on that side. And then we're going to calculate, obviously, the outputs. So in my case, when I plug in 2.9, because this is a piecewise defined function, I have to notice that 2.9 is less than 3. So I need to plug in the 2.9 into this top expression. So I need to take and do 2.9 and then add 2 to it, right? So that's going to give me a 4.9 when I type that in. The same thing with 2.99. We type it into the top expression, and you would get a 4.99. 2.999, again, that's less than 3, so use the top expression. X plus 2, or 2.999 plus 2, is 4.999. So we went from 4.9 to 4.99 to 4.999 when we went underneath of 3. Well, what if we go above 3? So let's type in 3.1 into the function. Well, if we do that, then what's going to happen is you're going to have to use this bottom expression, the 3x minus 1. So you're going to take 3 times 3.1 minus 1. You end up with an 8.3. If you type in 3.01, since 3.01 is still bigger than 3, we're going to use the bottom expression, and we're going to get 8.03. If I do 3.001, I end up with 8.003. So you can see that the limits aren't actually converging to the same number here. So on the bottom side, it's looking like these numbers are getting closer to 5. The outputs are getting closer to 5. On the top side, it looks like the outputs are getting closer to 8. And so what we would say is that means since they're getting closer to different numbers, this limit does not exist. Or the limit of function f of x as x gets closer to 3 does not exist. Now, notice that while the limit doesn't exist, I still could have plugged in the number 3. This has an equal to on the bottom one. So if I would have plugged in the number 3, I would have gotten an 8. So the limit doesn't exist, but the function value does. But the limit doesn't exist because we're not going towards the same number. Now, in terms of graphs, what this looks like, I've already graphed this piecewise defined function. The function looks like x plus 2 for x less than 3. So it looks like this straight line. And for x bigger than 3, it looks like this straight line here. So notice that as you travel along this curve from left to right, as you get closer and closer to 3, the function looks like it's going towards the 0.35, right? Looks like it's going towards the 0.35 as you travel left. But as you travel from the right, it looks like it's going towards the 0.38. So because these things don't match up, this limit does not exist. Now, not every single piecewise function is not going to match up. Sometimes they will. So there are occasions in which you can find the limit of a piecewise defined function, but sometimes limits of piecewise defined functions don't exist, at least, not at the place where they're cut off at. So what I'd like you to do is both numerically and then graphically type in try to find these limits here. Okay, so on your own, try to do that. And then I'll show you how to do those things. I'll also show you how to use these pieces here with the graphs. So how to make sure your graphs are only defined on certain portions of your x interval.